Hello everyone, my name is Louis Del Monte and welcome to Del Monte and Science. This is part 2 on the mysterious nature of light. Now in part 1 we talked about the quantized nature of light and that it started with Max Planck in 1900 when he began to explain the photoelectric effect and then went to Albert Einstein, who actually did explain the photoelectric effect, saying that it was the quantum of light, the energy of the quantum of light, that led to specific energies of the electrons given off. Now, how important was this discovery? Well, it turns out that we all remember Albert Einstein for his development of the general and the special theory of relativity. However, he won the Nobel Prize for the photoelectric effect. That was where he won the Nobel Prize. And he published that paper in 1905, along with the paper on the special theory of relativities, and several other very important papers. It was an outstanding year for science. 1905 was a golden year for science. A lot of new ideas and concepts were brought forth, and they became extremely important to modern science. Now we're going to talk about the second property of light that makes it mysterious. And that is that light. Now I want you to first just think about an inertial frame of reference. I've drawn it in two dimensions. An inertial frame of reference is any frame of reference moving at a constant velocity. So as long as the velocity is constant, this frame is called inertial. It's an inertial frame of reference. Now it can be a three-dimensional frame, a two-dimensional frame, etc. And the second property of light that's mysterious is that regardless of the velocity of the frame of reference, if I have in here a light bulb as my emission source with the filament, etc., and you screw it in. This is my emission source and it's giving off light. And we're just going to say that this inertial frame of reference is in a vacuum, that the speed of light, the speed of light, which is often designated by the letter C, is a constant. So that says no matter how fast I'm going, whether I'm standing still or I'm going very fast, that the speed of light in this frame is always a constant. And that's not intuitive. And I'll tell you why that's not intuitive. If you're in your car, okay, here you are in the car, okay, and you have a sunroof, and the car is going along at, say, I'm going to say 60 miles an hour. And you put your head out and you throw a baseball forward. You throw a baseball, here's a baseball going forward, and you throw the baseball so that it, when it left your hand, it had a velocity of 30 miles an hour. The sum total, because the car was going 60 and you gave a velocity, imparted a velocity to the baseball of 30 miles per hour, when the baseball is actually measured by someone in another inertial frame of reference, the baseball is actually going 90 miles an hour. And so you can prove this to yourself. You can simply be on your bicycle and throw a ball forward. And it'll go much further than you would if you were standing still and threw the ball forward with the same amount of force. Basically, it's additive. You add the speed of the inertial frame, the car in this case, to the speed that you imparted to the baseball, and it's additive, and you get 90 miles per hour. 90 miles per hour is a very fast baseball. That's about as fast as a major league pitcher pitches a fastball. It's between 90 and 100 miles per hour. So it's not intuitive that light would be a constant regardless of the speed of the inertial frame. However, this has been measured, and it turns out to be true. It turns out that light is a constant regardless of the speed of the emission source. So we're left with some very serious questions. And so why don't we list them? Why is light mysterious? Well, one, light has a wave-particle duality. Light has a wave-particle duality. And in quantum mechanics, it's typically assumed that matter and subatomic particles also have a wave-particle duality. This is an unusual property that light can act as both a wave and a particle. And one of the first solutions in quantum mechanics of the energy in an electron, the energy of an electron in a hydrogen atom, was the Schrödinger equation, which was a wave equation. The second thing is that the speed of light, which I'm calling c, which is this is very typical, is a constant in all inertial frames of reference. And third, that the speed of light c is the upper limit of speed in the universe. Okay, so they're saying the speed of light in a vacuum is as fast as anything can possibly go. Nothing goes faster than the speed of light in the vacuum. Now, these are the main elements that make light mysterious. We've learned an enormous amount of material about light. For example, we learned that the particle of light in about 1925 or so was confirmed to be a photon. So it's a packet of energy. However, you might think that the photon looks like this, a little round ball, and sometimes it's depicted more as a very concentrated wave. Okay, so there's that particle-wave duality. Here's another interesting thing. Light has no mass. So the photon, it has no mass. It's pure energy. So it has no mass, so we've learned that. And we've learned the speed of light. We said it's a constant in all inertial frames of reference. and we've got it down to a T. It's approximately, and you can look up the exact amount, but it's approximately 186,000 miles per second. That's how fast light travels in a vacuum. So I'm going to just conclude with this. We know a lot about light, you know, but we're a long way from understanding why it has a wave-particle duality. We don't understand that. We know it does. We can prove it does. We know that it's a constant in all inertial frames of reference, and we can prove that. We know its speed very exactly. If you look it up to many decimal places, we know its speed very exactly. It is a constant in all inertial frames of reference, and we have not seen anything go faster than light. It seems to be, and based on Einstein's special theory of relativity, that if you try to move any mass, something with mass, close to the speed of light, it becomes more massive, and the energy required to move it becomes almost infinite. So light is sort of the traffic cop of the universe. Now I'm going to leave you with one last piece of information, which is kind of an additional puzzle, but there is such a thing called the negative vacuum. And we see that in the Casimir effect, which I've discussed in a video, in some of the early videos. Light is believed to actually go faster in a negative vacuum than it does in our normal vacuum, our normal positive vacuum, which is yet another mystery. Thank you very much for joining me in this series.